So as usual, the best way to start this one is by drawing a diagram. So here's our x-axis, here's our y-axis, and here's our z-axis going up like this. And we've got a cube which has got vertices like this. So sorry about my poor drawing skills. And then we've got an electric field. The electric field is heading in the y direction, so like this, and it's got an x dependent. So the electric field lines are getting a little bit closer as we move along this x-axis here. And in the first part of the question, we're asked what's the electric flux through the entire cube. So to answer that, we can use that the electric flux is equal to E dot dA, which through a closed surface is given by the enclosed charge over epsilon naught, and there is no charge enclosed in this surface. None of the electric field lines are starting or ending inside the surface. So because there is no enclosed charge, the total electric flux through the cube is equal to 0. Now in the next part of the question, we're asked to find the electric flux through each of the sides of the cube. So it doesn't necessarily follow that because the electric flux through the entire cube is 0, that the electric flux through each of the sides is 0. Okay, so the first side we're asked about is 0, 0, 0, 2, 0, 0, 2, 2, 2, 0, 2, 0. So this bottom side here. Now, hopefully you can see with this bottom side, it is parallel to these electric field lines. So the electric field lines aren't actually cutting through this lower surface here. So for that first one, the electric flux is equal to 0. So the next side we're asked about is 2, 0, 0, 2, 2, 2, 2, 2, 2, and then what's this one? 2, 0, 2. So this side here. And again, you can see the electric field lines are parallel to this plane here. So they're not actually cutting through this plane here. So the electric flux for this side is also 0. Okay, next we're asked about the side with vertices 0, 0, 0, and then 2, 0, 0, and then 2, 0, 2, and 0, 0, 2. So this side here. Now with this one, we do have electric field lines cutting through the surface. So with this side, when we draw dA, it's always coming out from the surface. So it's got this direction here. So you can see dA is in the opposite direction to the electric field lines. And so the electric flux is given by the electric field dotted with dA. Now this question is further complicated slightly because the electric field strength depends on the x position. So what we'll do is we'll consider a little slice through this side here with a length dx, which is a distance x from this z-axis here. And so we can say, well, the area of the slice is given by the height, which is the z distance, so that's going from 0 to 2, so it's got a height of 2, and then it's got a width of dx. So this is dA, and we can see when we take the dot product between E and dA, they're anti-parallel, i.e. they're parallel but in opposite directions. So we can write this as minus the integral of E dA, with the dot product giving us that minus there because of the opposite signs. And now what we can do is we can substitute in. E, we're told in the question, is equal to 2 plus 1 x, and then dA we've said is 2 dx. So, and we should consider the limits on our integral too. X is going from 0 to 2 here, so from 0 to 2. So this is equal to minus from 0 to 2, and then we've got 4 plus 2x dx. When we integrate that, we've got 4x, we've got the negative still, plus, when we integrate this, we'll end up with x squared, and that's evaluated at 0 and 2. So substituting in, we've got minus 4 times 2, which is 8, plus x squared, which is 4. So this is equal to minus 12, and that is Newton meters squared per coulomb. Okay, so we've done 3 of the sides. The next side it asked us for was 0, 0, 2, and then 2, 0, 2, and then 2, 2, 2, and finally 0, 2, 2. So this top side here, so for this top side, that's also 0 because the electric field lines are parallel. Next, we have got this back side here, which is 0, 0, 0, 0, 2, 0, 0, 2, 2, and then 0, 0, 2. So this back side, once again, the plane is parallel to these electric field lines. They're not cutting through it, so it's 0. And then finally, we've got this side here. Now, in this case, dA is coming out of our closed object, so it's in the same direction as the electric field. So we can solve this side in exactly the same way as we did for this one, only now E and dA are in the same direction instead of the opposite direction. So we're just going to have a different sign here. So for this side, we end up with exactly the same thing apart from no negative sign. So this will be 12 Newton meters squared per coulomb. Now, of course, if we didn't want to solve it that way, we could have just realized that the total flux through the surface was 0. And since we've discussed every other side and only one of them had a non-zero flux, the flux through this surface is going to have to be equal and opposite to the flux through that other surface.